This video is going to show you how to do the calculations for a titration of a weak acid with a strong base. And so what we want to do here is we want to consider the titration of, okay, there's working, 50 milliliters of 0.10 molar acetic acid with 0.10 molar sodium hydroxide. And the Ka for acetic acid is 1.8 times 10 to the negative fifth. Now, like the last video, I'm going to do the same thing where I'm going to add increasing amounts of sodium hydroxide, and I'm going to select very specific volumes so that our pH curve that we graph will show us what it needs to show us. So the first thing we're going to do, the first situation is when we have 0 milliliters of sodium hydroxide added. Okay. So if we have no sodium hydroxide added, that means all we have is acetic acid. So we've got acetic acid plus water. Acetic acid is a weak acid, so it's going to be in equilibrium. I will get hydronium ion and acetate. And this is the only, I just have this dissociation. I don't have a chemical reaction because I've not added sodium hydroxide. So with 0 milliliters of base added, this is just like calculating the pH of a weak acid. So I'm going to put in the information that I know, and I have 0.10 molar acetic acid, and I have none of either of these. Now, if they had decided to give me a buffer for this problem, I would have some amount of acetate that I would be starting with here, but I don't in this situation, so I'm going to put 0 there. Because I have the Ka, I know that my product side will go up by X, my reactant side will go down by X, 0.10 minus X, X, and X. So then I will say that Ka is equal to 1.8 times 10 to the negative fifth. That's equal to x squared divided by 0.10 minus x. If I do Ka times 100, much less than this, so I can approximate. And I would leave, I'd write a note here, approximate, because Ka times 100 is much less than the initial concentration. So now I'm going to have x squared is going to be equal to 1.8 times 10 to the negative fifth times 0.1, which is 1.8 times 10 to the negative sixth. I'm going to do the square root of that, and I will get x equals 0.0013 molar for my molarities. That x tells me my hydronium ion concentration. So to get pH, I'm going to do negative log of 0.0013. And when I do that, I get 2.87, 2 sig figs. So I want 2 numbers after the decimal. So that's my pH at with 0 milliliters of sodium hydroxide added. Okay, so now I want to add some sodium hydroxide. So my second situation is going to be where I've added 10 milliliters of 0.10 molar sodium hydroxide to that existing acetic acid solution. So I'm going to move this over here because I want you to be able to see this. All right, so I go back. I have 50 milliliters of 0.1 molar acetic acid. So if I look, this is the equilibrium to which I am adding the sodium hydroxide. So I'm adding this strong base to it. Now, if you think about the lesson that we learned in class about buffers, when a strong acid is added to an equilibrium like this, it's going to react with the conjugate base. But when a strong base is added to an equilibrium like this, it's going to react with the weak acid. So what's going to happen is hydroxide is going to react with acetic acid. So I want to write that reaction first. So I'm going to write acetic acid plus sodium hydroxide. I can include the sodium ion. I don't have to. I think you guys probably will, so I'll include it. This is a strong base, so it's going to be a stoichiometry reaction. This will actually end up being my spectator. I'm going to get sodium acetate, so let's go ahead and just write that. I'm going to get rid of my sodium ion. Okay, and then I'll also have water. Now, in all of these problems, with what we showed you in class, the steps that we gave you, you are always going to do stoichiometry first. So this is my initial change final table, stoichiometry table. Not worry about water. So what I will do is I'll say, what do I have? And because this is a chemical reaction, I need to go to moles. So I was given 50 milliliters of 0.10 molar acetic acid. So I want to start with my 50 milliliters. I know I'm not doing sig figs. Milliliters to millimoles, and it was, I don't even remember, it was 0.1. So this is going to be 0.1. So I'm going to have 50 times 0.1, that's going to give me 5 millimoles. Remember, if you don't like millimoles, you can just do it with regular molarity. And then for my hydroxide, I'm going to do 10 milliliters times molarity. So 10 times 0.1 is 1 millimole, and I have none of the salt initially, or the conjugate. All right, so now what I do is I look at my reactants and I see that my hydroxide is limiting. So the reactant side will go down by 1 millimole, product side will go up by 1 millimole. I am left with 4 millimoles of my acetic acid. I have no hydroxide left, and I have 1 millimole of my conjugate. Now, because I combined two solutions, my volume changed. So what I must do now is I've got to divide by my total volume, which is 60 milliliters. So 4 divided by 60 gives me 0.067 molar. If I do 1 divided by 60, I will get 0.0167 molar. Okay, so here's my stoichiometry first. Now what I want to do is I want to go back to this initial equilibrium. Okay, so if I write my acetic acid plus water in equilibrium with acetate ion and hydronium ion, that's my initial reaction, I would set up an ice chart because it's stoichiometry first, equilibrium second, getting rid of my water. And then what I want to do is I want to look up here at what I did for stoichiometry, and I want to transfer what's left down here. Well, if I think about it, I don't have any hydroxide left. This is all gone. You know, I'm down, I have 0 left, so there's none there. So really, all I have left is water, which is not included. I have the acetic acid, which is 0.067, and I have the conjugate base, which is 0.0167 molar. Now at this point I have a choice. I can do Henderson-Hasselbalch, or I can do an ice chart. I'm going to do Henderson-Hasselbalch just because it's easier and it's faster at this point. So pH equals negative log of my Ka, which because it's acetic acid, 1.8 times 10 to the negative 5th, plus the log of the conjugate base concentration, 0.0167, divided by the concentration of the acid. So now I'm going to go ahead and do this. When I do negative log of 1.8 times 10 to the negative 5th, I get 4.87 plus the log of 0.0167 divided by 0.067, that quantity. When I do that, I get a pH of 2 decimal places after, because I started with 2 sig figs, 4.14. So that is my pH. All right, now what I'm going to do is probably need to write these down somewhere. So I'm going to do this as I'm working, because I'm going to go back and continually use the same things that we've done before. So, okay, so now what we're going to do is instead of 10 milliliters of sodium hydroxide, we are now going to add 25 milliliters of sodium hydroxide. Okay, so I need to get rid of work that I do not need. Okay, this is going to be different. Let's get rid of this and get rid of this and get rid of this. All right, so my amount of sodium hydroxide or acetic acid that I had initially to start with has not changed. That's still the same. But what has changed is my volume of sodium hydroxide. Now, just like we did before, when a strong base is added to an acidic buffer, that strong base is going to react with the weak acid. So we write a stoichiometry problem first. So I have acetic acid plus the strong base yields the acetate ion and water. So now what I want to do is, because it's a chemical reaction, I want to calculate moles of each. So I'm going to do 25 milliliters of 0.1 millimoles sodium hydroxide. That gives me 2.5 millimoles to start. If I look at this, I see that the hydroxide is limiting. So the reactant side will go down by 2.5 millimoles. Product side will go up by 2.5 millimoles. Now, if you were starting with a concentration here, you would just be adding 2.5 to that. So now on my final line, I get 2.5 millimoles for acetate. I get no millimoles for hydroxide, and I get 2.5 millimoles for acetic acid. So now I'm kind of at this special place, because if you notice, the moles of both my weak acid and my conjugate base are equal to each other. So if I divide by total volume, which is 75 milliliters, not only is my my number of moles the same, but my concentrations are going to be the same as well. So each of these are 0.033 molar. And I have no base left. So this is all gone. It's not there. It's been consumed. So now my stoichiometry is done. What I want to do is I want to take these numbers and I want to transfer them into that existing equilibrium that I had. So I'm going to take 0.033 molar and 0.033 molar. Whoops, I forgot my 3, sorry. Substitute them into my ice chart. So stoichiometry first, equilibrium second. Now, because I have both the weak acid and its conjugate base, I can use Henderson-Hasselbalch. Henderson-Hasselbalch has not changed in terms of the equation. All that's changed are my concentrations. So I'm going to go ahead and put those in. Well, the same, this is going to be 1. My ratio is going to be 1. The log of 1 is 0. So my pH is going to be equal to the negative log of 1.8 times 10 to the negative 5th. When I solve, I get a pH of 4.74. Now this is a special situation that I want to mention. If you think about this, what is true here is that pH was equal to pKa. When this is true, you are at what's called the halfway point. Oh wow, sorry. Didn't mean to do that, but I guess it works. So pH is equal to pKa at the halfway point, and that is where your concentrations of your acid and your conjugate base are equal to each other. The other thing I want you to notice here is that if you look at the amount, let's see if that'll go back. No, that just made it skinnier, sorry. Let me go back and fix this. Okay, if you look at the amount that this was changing by, it was changing by half of what you initially started with for your weak acid. So if you recognize that half of that is going to be gone, or that your amounts of weak acid and conjugate base, or weak base and conjugate acid, are equal to each other, then you know you're at the halfway point and pH is equal to pKa. So you could either do the calculation or you could just make a statement that this is true, and then go ahead and quickly do the calculation. All right, so now what we're going to do is we are going to continue. So what I want to do here is we are now going to do, instead of 25 milliliters of 0.1 molar sodium hydroxide, we are now going to do 40 milliliters. So let's say 40, and then we want to get rid of things that were still the same. Okay, so we'll get rid of this, we'll get rid of this, we'll get rid of these. pH will probably change. We don't need halfway point anymore because that was a special situation. Okay, so now what we're going to do is that strong base is going to once again react with the weak acid, but I need to go to millimoles. So I'm going to take 40 milliliters times my molarity. I'm going to get 4 millimoles. Okay, if you're looking at this, you're saying, okay, hydroxide's going to be limiting. This side will go down by 4. Product side will go up by 4. I'm going to have no strong base left. I'll have 1 millimole of acid present and 4 millimoles of conjugate base present. I need to divide by total volume, which is 90 milliliters. And I'll have 1 divided by 90. That's going to give me 0.011 molar. 4 divided by 90 gives me 0.044 molar. I'm going to substitute these in. Okay, once again, I can do Henderson-Hasselbalch because I have amounts of each of these. So I'm going to do the conjugate base divided by the acid concentration. So I'm going to do the negative log of my Ka plus the log of 0.044 divided by 0.011. That is going to give me a pH of 5.34. Okay, what I'm going to do is I'm going to stop this video because the next situation is going to be where we are at the equivalence point, and I want to do the last half of this titration in a separate video.